So we left off last time talking about buckling, and we developed the equation. We had a couple equations in general that are critical. Our P critical was equal to n squared times pi squared times EI divided by the length squared. And then we modified that a little bit and talked about, well, getting rid of the mode shape and dealing with that in terms of the effective length. And we talked then about the equation pi squared E times I to then K times L squared, where K was the effective length factor. And we finished up last time talking about that effective length factor. Well, I wanted to come back and whether we use this equation or whether we use this equation, I'll try and show you it's a really effectively the same equation. But I wanted to come back and practice a problem in this area. We certainly are not going to exhaust the subject of beams and buckling. It's a very big area, and purposely I wouldn't go very far into this even if we had more time, because the civils are going to want to treat this probably differently than maybe the mechanicals are going to want to. But we can start exploring this. So what I've got here to wrap up is this problem. We'd like to find the largest load that a W8 by 28 column. So that's a wide flange column like you see over there in the room there. W8 means that the dimension here is a nominal 8 inches. Okay, it may not be exactly 8 inches, but it's about 8 inches. We could look at that up in a handbook. And then if we were to cut off a 1 foot long section of it, it would be 28 pounds. So that gives us an idea of the thickness and the girth of that. Okay, and we'd like to figure out how much that can support without buckling. If the length is 36 feet, and we're going to mix it up a little bit. We're going to mix it up and say that we have first mode in the y direction and second mode in the x direction. So if we look at the cross section of this, I'm going to say that x is this way and y is that way. And sometimes we describe things that are unsymmetrical in both directions as weak axes and strong axes. So if I have it bending this way, that's going to be the strong way. That's going to be the hard way to bend it, right? Okay, there's people that specialize in rolling shapes, and they advertise that they can bend W 40 by 500 the hard way, or they can bend it the easy way. If I bend it this way, that's the hard way, right? If I bend it this way, that's the easy way. Okay? So one's going to have the maximum I value, one's going to have the minimum I value. So something to think about. So we'll put this column up into position here, and we're told that the length of this is 36 feet. And to give you some idea, this is the x direction here, and these hidden lines would be the web that you see here. So if we were to look at it from this view here, that would be exactly the same that we have looking at it this way. Okay. So if you had this X-ray vision, you could look through it and you could see that web there. And if we were to look up in a handbook, we would know that IX would be 98 inches to the fourth. And if this one happens to be in the back of your textbook, I don't know whether it is or not, that would be fine. Or you could look it up in the American Institute of Steel Construction handbook, and it would have these values. And IY, the minimum value, is 21.7. The cross-sectional area is 8.25. And we'll take the compressive stress as 24 KSI. We usually start with 36 KSI steel and put a safety factor on there. But we'll go with that, because we're probably going to want to not only check buckling, but just plain old compression. With something this tall, though, probably buckling is going to be way more restrictive. So we're going to have to do this twice to deal with the first mode in the y direction and deal with the second mode in the x direction. And this comes up quite a bit. You can imagine that if you had another beam attached to this, that might brace it really well in one direction, but not so well in another direction. So this is not a purely academic problem. So I'm going to start by analyzing. I'm going to talk about buckling about the x-axis in the y direction. Okay, buckling about the x-axis in the y direction, that's this one right here. Okay, so we're going to talk about that, and we're going to be using then the largest value for the moment of inertia. So I'll go ahead, and since we're talking about mode shape, I will use this equation up here, but I will also, before I'm done, try and relate it to the other one. So I'm going to say that the P critical on this thing is going to be equal to, what, 1 squared, which I wouldn't necessarily even need to write, then pi squared times E, which is, what, 30 times 10 to the 3, we're given as KSI, so I have to be careful with that, KSI, times I, which is the largest one, 98 inches to the 4th, and then I have to divide this thing by what? 36, that's the length, so 36 squared feet squared, which I'm going to have a units problem. We've got a lot of inches, and then all of a sudden we've got this foot here, so let's do 144 inches squared in a foot squared. So this is for units. So I can cancel that with that. And then I have the KSI, or I have this inches squared there with a couple of those, and I have the KSI with the others of those, and I'm left then with what? Thousands of pounds, right? Okay. So when you run through those numbers, you're going to come up with 155.5 thousand pounds, or 155 or 156 kips. Okay, so that's one number. We wouldn't want to start celebrating quite yet. We probably need to check the others. We would need to look, secondly, about what happens if it fails in this direction. Okay, so this would be the second way. 2 is to look at buckling about the y-axis in the x direction. And you might say, well, that's the weak direction, but remember, that one's braced. That's second mode shape. So it's going to look something like that. So we could say that our critical here is equal to, we're going to get to square n, so we've got n is equal to 2, so I'll have 2 squared, very good, 2, times pi squared, times e, which is 30 times 10 to the 3, KSI, times, now I use the lower value for I, 21.7 inches to the 4th, and I'm going to divide by, again, 36 squared feet squared, and for a units correction, again, 144 inches squared per foot squared. When you run through the math on this, this comes up with 137.7 kips. Okay, so even though it was braced in the middle, its I value was so much smaller, this appears to be critical, doesn't it? Okay, and you might say, well, what about this equation here? Well, we could have actually used that one, because by bracing this, what have we effectively done to our length here? Divided it by 2. So if you put a factor of 2 in there, would this be the, I'm sorry, we've reduced the length by a factor of a half. So if you put a half in there, would that be the same thing that we have up here with the 2 squared in the numerator? It actually would, wouldn't it? So you can see that. The last thing I should probably check is just pure compression. So I'm going to look at sigma being equal to, we've got sigma equal to force divided by area, so I could rearrange that and say that force P is equal to the sigma times the area, which, what do we have for sigma? We're going to use 24 KSI, so 24 kips per inch squared, times the area, 8.25 inches squared, gets me, what, 198 kips? Okay. So what's our answer? It's certainly not going to make it to 198 if it fails at 155, and it won't even make it to 155 if it fails here. So this would be the governing load, wouldn't it? Yeah, so that would be our answer. That's the critical value, 137,000 pounds. Okay. Questions with that? Well, that's probably a pretty good stopping point. I guess that, what do we do? I guess one more page here. We got to end this properly. So, what's that? That is all, folks. Okay, so